It's a set of equations that explains all particles and forces in the universe, allowing us to understand just about every phenomenon, past and present. I'm talking, of course, about the mythical theory of everything. Mythical because it has eluded scientists for decades, but there is a theory on the horizon that appears to be the missing link that explains not only the fabric of time and space, but also one of the biggest mysteries of existence, and that is, what came before the Big Bang? What is it, and what does it have to say about existence? That's coming up right now. The closest thing we have to an all-encompassing framework that explains all particles and forces is represented by the Standard Model of particle physics. But I showed in a previous video this model is flawed because it does not explain gravity. Gravity can only currently be modeled using Einstein's general theory of relativity. A theory of everything has to be able to reconcile quantum mechanics with the general theory of relativity. This reconciliation appears to be possible with a theory called loop quantum gravity, or LQG. The core mathematics of LQG are super complicated, but I'm going to simplify it as much as I can. According to Einstein, gravity is not a force, it is a geometric property of space-time itself. The theory of LQG attempts to show that this geometric fabric of space-time is not continuous as Einstein presumed, but is itself quanta, made up of discrete quanta. This is akin to the clothes or sweater you might be wearing right now. Even though it looks smooth from far away, if you looked at it closely, you would see threads, nodes, and loops woven together. These are the quanta or bits that your clothing is made of. Space-time is similarly not smooth at the smallest scale according to LQG. Now this is different than every other theory, including string theory, because even in string theory, space is the background or the canvas on which strings vibrate. In LQG, this space-time background is itself quantized, like your clothing or your television. So this means that distance has a minimum quantity, about equivalent to the Planck length, or 10 to the negative 33 centimeters, and volume has a minimum value of 10 to the negative 99 centimeters cubed, below which it cannot go. Now this is super tiny. To give you an idea of the smallness of the scales we're talking about, LQG says that there are about 10 to the 99 quanta of volume every cubic centimeter of space. This quantum value is so tiny that there are more such quanta in a cubic centimeter than there are cubic centimeters in the entire visible universe. And time itself has a minimum quantity as well, which is 10 to the negative 43 seconds, or close to Planck time. And what do these space-time quanta look like? Well, you can't really visualize it, but conceptually, the clue is in the name loop quantum. Space-time is actually made up of finite loops. The nodes that intersect is where the quanta volumes of space reside. It has a volume that is a multiple of the Planck volume. The loops in between the nodes represent two-dimensional areas, and large quantities of these loops and nodes are called spin networks. Space is defined by the geometry of this spin network, and time is defined by the moves that rearranges this spin network. The spin network, when combined with these quantum movements of time, is called a spin foam. Time does not flow like a river in the spin foam, it ticks like a digital clock. And each such quantum tick or movement of the spin network is 1 times 10 to the negative 43 seconds. Every location in the spin network where a quantum move takes place, time has ticked once. How do particles traverse this quantized space? When mass and energy are added to the spin foam, the shape of the volumes of the spin network are distorted. This distorts space and time because any movement of these quanta also affects the time quanta. Time is essentially movement of these volume quanta, and this distortion of space and time is what we perceive as gravity. The spin network is unimaginably large. If we could draw a detailed picture of the spin network of our universe, it would consist of approximately 10 to the 184 nodes. The exciting thing about QLG is that it appears to explain some of cosmology's greatest questions, like what came before the Big Bang? According to LQG, the Big Bang could not have started with a singularity, which would have been infinitesimally small and of infinite density, because there's a limit to how small space can become, 10 to the negative 99 cubic centimeters. This is the smallest volume of space according to LQG. This also implies a maximum energy density that this minimum volume of space could have had, And once that maximum energy density was reached, it would have repelled any additional energy added to it. Like a sponge that gets saturated with water will repel any additional water. So LQG predicts that the universe did not start with a Big Bang, but something called a big bounce. The universe was big at one time, it then contracted, it bounced, and then exploded from this bounce. So prior to what we call the Big Bang, the universe was in a contracting phase of a prior universe. And when it reached a minimum Planck volume, all additional energy bounced off and created what looks to us like a Big Bang. So LQG has a lot going for it. Is it the theory of everything? No, not quite yet, because it needs to be confirmed with observation. And its mathematics needs to be further developed to make dark energy and dark matter emerge. But in my view, loop quantum gravity has brought us closer to a theory of everything than just about anything else over the past 100 years.